Hey, Alex, Miss Johnson. I can't get my webcam to work, and I'm not going to try today. So you don't get my face in the corner, but I assure you, it's still me. I'm still here. We're still doing calculus. Let's get to it. All right. Introduction to derivatives. We talked about this a little bit in Unit One, where we're interested in physics and in different sciences, and of course, mathematicians are just interested for fun about being able to find the slope of an equation at a single point. So generally, when we're asking for slopes, we're asking for the slope of a linear equation, something like the red example, where at any point we say, oh, the slope is 1, right? M equals 1, because this is mx plus b, m equals 1. And then the way we'd kind of see it is when we're moving along the function, we do rise over run, and it shows you how steep the function is. Nice. We want to be able to talk about this when our equation is not just a straight line, right? We want to be able to talk about this when we've got curvy equations. And that generally looks like, if I'm looking for the slope at a point here, we're going to draw in a tangent line. I'm going to write that in a second. A tangent line is just, that doesn't look like tangent. A tangent line is a line that just touches the function. It just like touches it once at a single point. So that's the tangent line for, say, -1. The tangent line here just touches it once. And what we're going to notice about tangent lines is if it just touches, just kisses it once kind of thing, we kind of get to talk about the steepness at any certain point of our green function by talking about the slopes of these tangent lines that are associated with them. This is not like a super easy task. We need some pretty high-duty mathematics for that, heavy-duty mathematics, which is what a derivative is. It is a way to take an equation and write another equation for its slopes. We are going to find some rules for that, figure out that process, understand how we build up that mathematics, and we're going to start doing that today. All right, so again, we're trying to find the slope of these tangent lines. And basically the way people thought of doing this would be, okay, if I picked a point kind of close, like I'm looking for this line, right? The one that just, actually, let me do it like this. I'm looking for this line. It's the one that just touches the line once at the black point at x equals 2. The way to do this is maybe pick another point on the line that's a little bit close. Oh, that one should be black. This is going to mess up everything. Fine. Pick a point kind of close, so I'll pick 3. And draw what we call a secant line. A secant line is, instead of touching exactly 1 point in a function, it's touching 2. That's fine. This is a fine estimation for the slope at the black point by going through 2 points. But what would make it a better estimation is if we picked a closer point, right? If we picked 2.5 instead of 3, now all of a sudden the slope of the green line, let's make it better. The slope of the green line looks a little bit closer to what we would actually expect to happen at the black point. And then we can keep doing this. We can keep picking closer and closer points to make our estimate get better and better. If we picked 2.1, for instance, this slope is looking more and more like what we'd expect from actually the slope of the tangent line, which is something like this line. That's just awful, y'all. No, I'm going to do it with line function, even though I really don't want to. Like the blue slope and the black slope are pretty similar. So as we plug in points closer and closer to our target point, we are getting tangent lines that look more and more like the actual tangent line. Secant lines that look more and more like the actual tangent line. Going back to algebra 1, we've got a slope equation. If we wanted to find the slope of the red line, the slope of the green line, the slope of the blue line, so we can estimate the slope of the black line, we would just use this equation. We would find the y values for each of these. So I said 2 matches with 10, 3 matches with 7, 2 matches with 10, 2 matches with 10. 2.5 I said was 9, and then this one I said was 9.8. If I gave you an equation, you would just plug these numbers into the equation, and I'm going to do an example of that at the back. in order to find these slopes, you get out a calculator, you get out Desmos, you get out your Siri, phone, whichever you like. And I'm just going to go ahead and plug in. Y2 is 7. Here's what I'm plugging into my calculator. So I'm finding the slope of the red line first. I'm doing 7 divided by 10 over 3 divided by 2. Sorry, 3 minus 2. I don't know what I said. But that's what I mean. And I get that this is negative 3. All right, so the slope here is negative 3. If we do our calculation for this one, we do our y2 minus y1 over x2 minus x1. We would get, this is now a 9. This is now a 2.5. We get negative 2. We go again for blue. We do 9.8 over 2.1. Oh, we also get negative 2. That's very funny. So whenever we pick closer and closer points, we're assuming that our slopes get closer and closer. If we want an even better estimate, we'd plug in 2.01, 2.0001, 2.000001, right? And we're getting closer to what our slope actually is at this point. All the numbers I've plugged in so far are bigger than 2. We could also do less than 2. We could have plugged in a 1. We could have plugged in 1.5. We could have plugged in 1.9, etc., and get closer and closer and closer. But with this, getting closer and closer means the distance between these 2 points is getting smaller and smaller and smaller, right? Here, the distance between 3 and 2 is 1. Here, the distance between 2.5 and 2 was 0.5. Here, the distance between our 2 points was 0.1. What we really want is for this distance to go to 0. And this is where limits come in. And you're thinking, oh, nice, finally, a chance to use limits. What we're saying is we want to be able to plug in 2 and something really close to 2, right? Where this number, the thing that we're adding onto 2 to make it close but not the same, is going to 0. We would then plug in 2 and plug in 2 plus h, the point close. Our slope would then be the y sub 2 minus the y sub 1 divided by x sub 2 minus x sub 1. And then 2 plus h minus 2, these cancel, and we just get h on the bottom. And we're saying this slope calculation is super accurate when h is very small, right? Here, h would have been 1 because we're adding 1 to get here. Here it would have been, again, 0.5. Here it would have been 0.1. And we're trying to make this h, the thing we're off by, very, very small. And that kind of zooms in on our derivative and zooms in on our actual slope. So yeah, we're going to come down here, and this I'm going to say 1,000 times. So if you don't get it this time, that's all good. But try to start wrestling with this so we can start asking questions that point you towards understanding. The derivative of function is an equation that gives you the slope at any point, and the derivative at a single point is the slope at that single point. The way we find the derivative is we basically do the slope equation, right? We do the slope equation where we're plugging in x plus h and x, aka something and something very close to it. And then we're making the distance between those 2 points go to 0, go to nothing, right? And that is the idea up here, where we're saying as we get closer and closer, these colorful lines are getting closer to actually just being the solid black line that we want. So as the distance between the x decreases, our lines are getting closer to what we're actually after. And that's why we're taking the limit as it approaches 0. All right, y'all, that's the intro to the philosophy of derivatives and why we're able to find this point, how we're able to find this point. Let me give you some examples about what's going on for your work today. What's happening is you're given a function. You're trying to find the slope at, I said 4, but I guess I mean 2. That's fine. So what we're going to do is we're going to plug in 2 and 2.1. So 2 points kind of close to each other. We're going to get even closer by plugging in 2.01. We're going to get close, but on the other side, we're going to plug in 1.99. And then we're going to do this kind of theoretical thing and plug in an h so we can get used to algebraically being able to find the simplification of this, the difference quotient. And then in later classes, we'll take the limit and actually find the derivative and find the exact slope. But we'll be able to estimate it pretty well from this. So I'm going to say this is green, this is red, and this is blue, just for purposes of being able to organize my notes. So first things first, I'm going to go into my calculator, or I'm going to go into Desmos, and I'm going to plug in my function with a bunch of parentheses so that I can plug in a bunch of these super fast. Actually, let me do it on Wolfram Alpha so that y'all can see it. Wolfram Alpha. Okay, what I'm going to do is the function is x squared plus 3x plus 2. I've got something squared plus 3 times that something plus 2. Accurate. And I want to plug in 2, so I'm going to go back here and put 2 into both of my equations. It equals 12. Thanks, Wolfram Alpha. I'm going to write a 12 on all of these. I'm going to go back and I'm going to say, actually, I want 2.1. I don't want 2. Then Wolfram Alpha is going to tell me, without too much more work, that it's 12.71. I love that about that. And now I'm going to say, actually, I want this to be 2.01. This is why I put in the parentheses so that I can quickly change out my input. I get 12.0701, 12.0701. And then for my last one, I want 1.99. I go back here, I go to all my parentheses, I change them to 1.99. 1.99. And I get 11.9301. 11.9301. Is that the case? Yes. Nice. And then over here, for my purple theoretical one, we're going to do that in a second. Let me do all these slope calculations for the non-theoretical ones first, so we can kind of estimate where this slope is getting closer to. When I go here, I am plugging these 2 points for all of my my examples into the slope equation. The slope equation is, again, the second y minus the first y divided by the second x minus the first x, where you can pick whichever point you want for the x's and y's. I am going to, as you might imagine, use Wolfram Alpha. I'm going to do something minus 12 and something minus 2. Because for all 3 of these, 12, 2 is my first point. I'm going to go ahead and plug those in for this, for my pattern. And now I'm going to come back and say, okay, it's 1271 and 2.1 for this one. So I'm going to type in 1271 and 2.1. And I get my slope is 7.1. Nice. For this one, my first point does not change out, but my second point does. I'm now plugging in 2.01 and 12.0701. So I'm going to change this to a 0701. I'm going to change this to a 2.01. And I'm going to get that my result is 7.01. Nope, because I want it to be red. And now I'm going to plug in my other point just to see what's happening on the other side. I've got 1.99 and I've got 11.9301. $11.9301. And I get 6.99. Nope, come on. 6.99. So if we had to estimate based on this, what is the exact slope at x equals 2? That's an at sign. I know y'all don't believe me because it doesn't look like it. At x equals 2. It's reasonable to guess that it's 7. Right? Both of these numbers are getting closer to 7 from the right and the left. The limit seems to be approaching 7. And we will get better at, or we will find a method to actually finding the exact thing and proving it. And that method is going to be locked up in being able to do this calculation, right? Whenever I say x is 2, what's y, I plugged in 2 to this equation. Whenever I say x is 2 plus h, what is plugging in 2 plus h here? This is like part 5 of your portfolio 1. This is saying every time I see an x, instead I'm going to plug in a 2 plus h. And then I like to simplify things to make them easier to deal with. I'm distributing. I'm simplifying my terms. I get h squared. 4 plus is 7h plus, and then this is 4 plus 6 plus 2 is 12. So I get this is my y term when I plug in 2 plus h. And then when I find my slope of this, I would say y2 minus y1 x2 minus x1. And then I'm going to simplify this a little bit. These two cancel out. These two cancel out. So I get h squared plus 7h divided by h. Because I can cancel an h from all 3 terms, I get to. And this simplifies to h plus 7. Now, if we scroll up here and say, what's the derivative? It's when h approaches 0. So if I said over here, what is the limit as h approaches 0 of 7 or h plus 7? I get to plug in a 0 for h. I get 7, and lo and behold, our slope at 2 is actually 7. All right, y'all. Give it your best shot at your getting closer assignment. Email me if you need help. Come to office hours this afternoon if you need help. I'm here for you. All right, take it easy.